4 human beings. 1 capsule, 400,000 kilometers of absolute nothing between them and the only world they have ever known. This is not a metaphor. This is not a simulation. This is Artemis II, the first crewed mission to leave Earth's gravitational embrace in more than 50 years. And buried inside the engineering reports, the radiation logs, the mission timelines, and the quiet conversations between NASA flight directors, there is a question that no press release has fully answered. What if something goes wrong out there? Not in low Earth orbit, where a rescue is theoretically possible. Not on the International Space Station, where a crew can shelter, wait, adapt. Out there, beyond the protective magnetic cocoon of this planet, in the deep black between worlds, where no human being has traveled since December 1972, where the physics of survival become unforgiving in ways that the human body was never designed to tolerate. Space does not negotiate. It does not warn. It does not hesitate. The Van Allen belts, those invisible walls of magnetically trapped radiation encircling Earth, are not a romantic astronomical feature. They are a lethal architecture. Billions of high-energy particles cycling endlessly through corridors of space that the human body must cross to reach the moon. And Artemis II will cross them, slowly, deliberately, for hours. The Orion capsule's shielding is real. The engineering is serious. The calculations have been run thousands of times by brilliant people under immense pressure. But radiation does not care about calculations. It penetrates. It accumulates. It damages DNA strands with a quiet efficiency that no amount of aluminum and polyethylene can entirely stop. And radiation is only one variable in a mission that carries dozens. 50 years ago, the last astronauts to leave Earth's orbit came home. But the margin between their survival and catastrophe was thinner than history remembers. Apollo 13 did not end in tragedy by luck, and by the kind of human improvisation that cannot be engineered in advance. 3 men, a crippled spacecraft, and a return trajectory calculated on the edge of panic. Now 4 people are preparing to make that same crossing, into the same darkness, trusting the same fundamental physics. But this time, the world has forgotten what it costs. This is the story of what NASA is gambling, what it knows, what it cannot guarantee, and what 4 human lives look like against the scale of a universe that has never once bent its laws for the sake of ambition. There is a number that defines the boundary between everything humanity has ever known and the vast indifference of deep space. That number is approximately 62,000 kilometers per hour. That is the speed at which the Orion capsule must travel to break free from Earth's gravitational grip and begin its transit toward the moon. It sounds like an abstraction, a figure in an engineering document, a line in a mission profile. But consider what it means in human terms. At 62,000 kilometers per hour, the entire continent of North America disappears behind you in less than 7 minutes. The curvature of the Earth, which astronauts in low orbit spend months admiring through porthole windows, becomes irrelevant within the first hour. The planet itself, 4.5 billion years of geology, biology, history, memory, and love, shrinks into a marble. And then, if you travel far enough, it becomes a point of pale blue light, indistinguishable at first glance from the stars surrounding it. Carl Sagan once described that image. Earth photographed from 4 billion miles away by Voyager 1 as a mote of dust suspended in a sunbeam. Artemis II will not travel 4 billion miles. It will travel roughly 400,000 kilometers. And yet, at that distance, The psychological transformation is total. The crew of Artemis II will become, for the first time in half a century, genuinely alone in a way that no human language was built to describe. This is not loneliness in the terrestrial sense. The loneliness of an empty apartment, a silent phone, a crowd that does not see you. This is geometric isolation, the kind that can be measured in light seconds. The kind where the signal you send home takes more than a second to arrive, and the reply takes another second to return. A 2-second delay may sound trivial, but in a spacecraft emergency, a pressure leak, a system failure, a medical crisis, 2 seconds is the difference between a question answered and a decision made alone. And decisions will be made alone. They must be. Because at lunar distance, no ground controller can reach in and fix what is breaking. The crew is sovereign in the worst possible way, not empowered by choice, but by necessity. Everything that goes wrong becomes their problem in real time, with the tools they have on board, and nothing else. This is the first weight of Artemis II that history tends to overlook. Not the radiation, not the trajectory, not the hardware, but the cognitive and psychological architecture required to remain functional human beings while suspended in an environment that is actively trying to kill you. 400,000 kilometers from the nearest breathable air. The human nervous system was not designed for this. It evolved over millions of years on the surface of a planet with gravity, atmosphere, magnetic shielding, and the constant sensory confirmation that the ground is beneath you and the sky is above. Remove all of that simultaneously, and the body begins to revolt in subtle, insidious ways. Fluids shift upward in microgravity, increasing intracranial pressure and distorting vision. The vestibular system, the inner ear's mechanism for spatial orientation, loses its reference frame entirely and begins sending contradictory signals to the brain. Nausea, disorientation, and cognitive disruption follow. These are not hypothetical risks. They are documented physiological realities experienced by every human being who has ever left Earth's surface. What is less documented, because so few humans have ever traveled beyond low Earth orbit, is how these effects compound at lunar distance. In a smaller capsule, with less living volume per person, under higher radiation exposure, with no possibility of early return. The Orion capsule has an interior, habitable volume of approximately 9 cubic meters for 4 people, for 10 days. 9 cubic meters is roughly the size of a large walk-in closet. Imagine 4 adult human beings, trained, disciplined, brilliant, physically exceptional, confined to that volume for 10 days while their bodies revolt. Their reference frames dissolve, and the black outside their windows contains no horizon, no landmark, no horizon line, nothing that the human visual cortex recognizes as safe. And yet, they will go. Because this is what exploration demands. Because the cost of not going, of leaving the moon unvisited, of surrendering deep space to inertia and fear, is its own kind of catastrophe, measured not in lives, but in centuries. There is a philosophical tension at the heart of every crewed space mission that engineers and mission planners rarely articulate directly, because to articulate it is to acknowledge something deeply uncomfortable. The tension is this: human beings are extraordinarily fragile biological systems operating in an environment so hostile that every moment of survival requires active mechanical intervention. The suits, the capsule, the life support systems, the thermal regulation, the pressure management. These are not enhancements. They are substitutes for everything the universe forgot to provide. A spacesuit is not armor. It is a portable atmosphere, a thin membrane of layered materials separating a living body from a vacuum that would cause the moisture on the surface of the eyes to begin boiling within seconds of exposure. Not dramatic Hollywood boiling, quiet, immediate, irreversible cellular destruction as the pressure differential tears dissolved gases out of biological tissue with the mechanical indifference of a physical law. The vacuum of space does not hate you. That is the most unsettling part. It does not want to destroy you. It is simply the default state of the universe. A near-perfect emptiness punctuated by occasional matter, occasional radiation, occasional gravitational fields. Life is the anomaly. Consciousness is the exception. And everything that keeps 4 human beings alive aboard Artemis II is a machine's argument against the universe's default preference for emptiness. This is the philosophical weight that sits beneath every mission patch, every press conference, every countdown clock. NASA does not gamble carelessly. The engineers who designed Orion are not reckless. The flight directors who approved this mission are not naive. They are people who understand exactly what they are doing, which is sending 4 fragile, irreplaceable human beings into an environment that will spend every second of that journey trying, passively and without malice, to end them. And they have calculated that the probability of success is high enough to justify the attempt. That calculation is not a comfort. It is a statement of mathematics applied to human life. And the history of spaceflight, the history written not in the successful missions, but in the ones that failed, is a history of calculations that were correct until they weren't, of probabilities that held until the one time they didn't, of systems that performed flawlessly through 1,000 tests, and then, once, at the worst possible moment, did not. Challenger was not destroyed by negligence alone. It was destroyed by a decision made within acceptable risk parameters that turned out, on a cold January morning, to be catastrophically wrong. Columbia was not lost to carelessness. It was lost to a piece of foam insulation, a material chosen and tested and approved, that struck a thermal protection tile at a velocity that the models had underestimated. In both cases, the math was not fraudulent. The math was incomplete, and the universe, indifferent as always, filled in the missing variables. The gap between a successful mission and a tragedy is not always ignorance. Sometimes it is the irreducible uncertainty of complex systems operating at the edge of human capability. And Artemis II is, by any honest measure, a complex system operating at the edge of human capability, carrying 4 lives into a regime of space that no human being has entered in more than 50 years. 50 years is not a long time in geological terms. It is not even a long time in the history of aviation. But in the history of spaceflight, 50 years is an eternity. The engineers who designed Apollo are gone. The institutional memory of lunar transit, the hard-won, blood and sweat knowledge of what it actually feels like to send people beyond Earth's protection, has faded. What remains are documents, recordings, telemetry data, and the fading testimonies of the 12 men who walked on the moon and the dozens more who orbited it. Artemis II is not starting from zero, but it is not starting from full knowledge either. It is starting from a reconstruction, a careful, intelligent, well-funded reconstruction of capabilities that were allowed to atrophy for half a century. While humanity's attention turned to low Earth orbit, to space stations, to the practical business of living in space rather than the audacious business of going somewhere in it. The Orion capsule is more advanced than Apollo in almost every measurable way. Its computers are incomparably more powerful. Its life support systems are more sophisticated. Its abort capabilities are more robust. And yet, it carries the same fundamental vulnerability that Apollo carried. The vulnerability of being a sealed metal and composite shell filled with 3 breathable gases, operated by biological creatures in an environment that tolerates none of those things. The universe is not impressed by engineering advances. It applies the same laws to Orion that it applied to Apollo 13. The same vacuum, the same radiation, the same gravitational mechanics, the same thermal extremes. The sunlit side of the capsule exposed to temperatures exceeding 120 degrees Celsius, while the shadowed side plunges below -150. The same electromagnetic silence beyond the reach of Earth's magnetosphere. What has changed is human knowledge and human technology. What has not changed is the fundamental asymmetry between the cosmos and the creatures brave enough to cross it. There is a killer that has no face. It carries no weapon that the human eye can detect. It leaves no visible wound on entry. It does not announce itself with pain or heat or sound. It passes through the walls of spacecraft and the walls of the human body with the same casual indifference, depositing its energy in the nucleus of living cells, rewriting the molecular instructions that keep those cells functioning, and then moving on, leaving behind a kind of damage that may not manifest for days or weeks or decades. It is called ionizing radiation, and beyond Earth's magnetic shield, it is everywhere. To understand what the crew of Artemis II will face, you must first understand what protects you right now, in this moment, wherever you are on the surface of this planet. The Earth is surrounded by a magnetic field generated by the churning of liquid iron in its outer core. A geodynamo running on the heat left over from the planet's formation 4.5 billion years ago. This field extends tens of thousands of kilometers into space, deflecting the vast majority of high-energy particles streaming outward from the Sun and inward from the galaxy. It is invisible, odorless, and utterly fundamental to the existence of complex life on this planet's surface. Without it, the solar wind, a constant stream of charged particles ejected from the Sun at speeds between 400 and 800 kilometers per second, would have long ago stripped Earth's atmosphere away, as it stripped Mars. The red planet lost its magnetic field roughly 4 billion years ago, and with it went its oceans, its thick atmosphere, and any realistic prospect of surface life. Mars is now a frozen, irradiated desert. And it is a desert in large part because the invisible shield that Earth still possesses simply stopped working there. The crew of Artemis II will leave that shield behind. They will pass through the Van Allen belts, 2 concentric zones of magnetically trapped radiation encircling Earth, and emerge on the other side into a region of space where the only protection from the Sun's particle output is the hull of the Orion capsule and the tissue of their own bodies. The Van Allen belts themselves deserve a moment of full contemplation because they are among the most extraordinary and least discussed structures in the near-Earth environment. The inner belt extends from roughly 1,000 to 12,000 kilometers above Earth's surface and is dominated by high-energy protons, particles stripped from hydrogen atoms and accelerated to fractions of the speed of light. The outer belt, extending from roughly 15,000 to 30,000 kilometers, is dominated by electrons energized to similarly extreme velocities. Together, they form a radiation environment so intense that spacecraft transiting them must do so quickly or risk catastrophic damage to both electronics and crew. Apollo missions took roughly 30 minutes to transit the belts at high velocity. Artemis II will follow a similar strategy, but 30 minutes inside a region of space where the radiation dose rate can reach thousands of times the natural background level on Earth's surface is not a trivial biological event. It is a calculated exposure, a price paid in cellular damage for the privilege of reaching lunar distance. The human body is remarkably resilient in many ways, but it was not designed to absorb high-energy protons and electrons. When a proton traveling at a significant fraction of the speed of light passes through biological tissue, it does not simply bounce off cells or slip between them. It interacts, depositing energy along its track, ionizing atoms within the molecules it encounters, breaking chemical bonds, and in the worst cases, snapping both strands of the DNA double helix simultaneously. A single strand break in DNA is usually repairable. The cellular machinery that maintains genetic integrity is sophisticated and efficient, honed by billions of years of evolution. But a double-strand break, both sides of the ladder severed at once, is a different category of damage. It can lead to misrepair, to chromosomal rearrangements, to mutations that alter the behavior of the cell in ways that may not become apparent for years. This is not speculation. This is radiobiology, a field built on decades of research involving cancer patients, nuclear workers, atomic bomb survivors, and increasingly, astronauts. The data is clear and consistent. Ionizing radiation at sufficient doses and energies causes DNA damage, increases cancer risk, accelerates certain aspects of aging, and at extreme doses, causes acute radiation syndrome, a systemic biological collapse that begins with nausea and fatigue and progresses, in severe cases, to the failure of the bone marrow and the immune system. The doses expected during Artemis II are not in the range of acute syndrome. The mission planners are not sending 4 people to their immediate deaths. But the cumulative radiation exposure of the 10-day mission, including the Van Allen belt transits, the period of free space travel beyond Earth's magnetosphere, and the proximity to the Moon's unshielded surface, will be substantially higher than any dose accumulated by astronauts aboard the International Space Station in a comparable period. The ISS orbits at approximately 400 kilometers altitude, still well within Earth's magnetic protection. Astronauts there experience radiation doses roughly equivalent to receiving a chest X-ray every single day. That is not zero risk. Long-duration ISS missions carry measurable increases in lifetime cancer risk. But it is a risk that exists within the partial shelter of the magnetosphere. Beyond it, the dose rates increase by factors of 2 to 3 under normal solar conditions, and solar conditions are not always normal. Here is where the risk calculus of Artemis II becomes genuinely difficult to resolve with certainty. The Sun is not a stable, predictable energy source. It is a thermonuclear furnace 400 times the diameter of Earth, with a magnetic field of its own that periodically becomes tangled, stressed, and violently unstable. When that instability releases, in the form of a solar flare or a coronal mass ejection, it sends a wave of high-energy particles and magnetized plasma outward through the solar system at speeds that can exceed 2,000 kilometers per second. A significant solar energetic particle event, the technical term for a major radiation storm driven by solar activity, can deliver doses to an unshielded astronaut in deep space that enter the range of acute radiation syndrome within hours. The largest solar particle event in recorded history, the Carrington event of 1859, was so energetic that it produced auroras visible at the equator and set telegraph wires on fire through induced electrical currents. A comparable event today would be catastrophic for both Earth's technological infrastructure and any crew caught outside the magnetosphere without sufficient shielding. The Sun is currently near the peak of solar cycle 25. The years surrounding a solar maximum are statistically the most active period of solar energetic particle events. The period when the frequency and intensity of flares and coronal mass ejections reaches its highest level in the 11-year cycle. Artemis II is being flown directly into this window. This is not a secret. The mission planners know it. The crew knows it. The flight surgeons who will monitor radiation exposure in real time know it. And the Orion capsule does carry a designated storm shelter, a confined area of the vehicle where additional shielding material and water, which is an effective radiation absorber, can be used to reduce dose rates during a particle event. But no storm shelter is perfect. No amount of shielding can entirely eliminate the risk when the source of the radiation is a star 93 million miles away, releasing energy equivalent to billions of nuclear weapons simultaneously. The most honest statement that can be made about solar radiation risk during Artemis II is this: the probability of a catastrophic particle event during the specific 10-day window of the mission is low. But it is not zero. And the difference between a low probability and zero is, in the architecture of human survival, everything. Consider the analogy of a lightning storm. The probability of being struck by lightning on any given walk across an open field is extremely low. The meteorological conditions, the geometry of the path, the duration of the exposure, all of these factors combine to make the individual risk small. But if you send 4 people across that field during an active thunderstorm, at the peak of storm season, and you tell their families that the probability of a strike is acceptably low, you have said something that is statistically true and humanly incomplete, because you have not accounted for the specific character of what it means to be the person struck by the one bolt that falls. The radiation environment of deep space does not operate on human timescales or human probability frameworks. It operates on the timescales of stellar physics, on the scale of magnetic reconnection events that release more energy in seconds than humanity has produced in its entire industrial history. Against that scale, the 10 days of Artemis II are an eye blink, a brief, fragile crossing through a regime that was old beyond comprehension before the first amino acid ever assembled itself in a warm ocean on this planet. And yet, buried in the radiation data, in the mission risk assessments, in the quiet conversations between flight surgeons and crew members, there is something that does not appear in the official documents. It is the knowledge, held by everyone involved and rarely spoken aloud, that the acceptable radiation limits currently used for NASA astronauts were not designed with lunar transit missions in mind. They were built around low Earth orbit operations, around ISS crews, around a paradigm of spaceflight that had not seriously contemplated sending human beings beyond the magnetosphere for 5 decades. Artemis II is, in a very real sense, generating data that the existing risk frameworks were not built to interpret. The mission will teach NASA things about human radiation exposure in deep space that cannot be fully known until the mission is flown. And 4 people are the instruments through which that knowledge will be collected. This is the unspoken contract at the center of human spaceflight. It has always been there. The astronauts of Mercury, Gemini, and Apollo signed it without fully knowing what they were signing, because the science did not yet exist to tell them. The crew of Artemis II signs it with more knowledge, more data, more models, more sophisticated risk assessments. But with the same fundamental uncertainty that has always defined the boundary between courage and calculation. They know what they are entering. They know what the sun can do. They know that the Van Allen belts will pass their energy through the walls of the capsule and into their cells. They know that beyond the belts, there is no shield, no shelter, no magnetosphere. Only the thin skin of an engineered capsule and the immeasurable silence of a universe that does not distinguish between a spacecraft and a grain of dust. And they have chosen to go anyway, not because they are indifferent to risk, but because they understand, perhaps more viscerally than anyone, that some knowledge can only be purchased with physical presence, that some thresholds can only be crossed by crossing them, that the question of whether humanity belongs in deep space cannot be answered from the safety of the surface. The radiation will be there when they arrive. The sun will be burning, the particles will be streaming, and 4 human beings, wrapped in engineering and courage in roughly equal measure, will be moving through it at 62,000 kilometers per hour, carrying the weight of a species that has always reached for things it was not entirely sure it could survive. There is a question that engineers ask when they design a vehicle meant to carry human beings into dangerous environments. It is not the question that appears in the mission overview documents or the press briefings. It is the question asked in the quieter rooms, in the failure mode analysis meetings, in the late sessions when the coffee has gone cold and the whiteboards are covered in diagrams of things going catastrophically wrong. The question is simple. It is 4 words long. What do we do? What do we do if the engine fails? What do we do if the pressure drops? What do we do if a micrometeorite, a fragment of ancient solar system debris traveling at 20 kilometers per second, finds the 1 square centimeter of hull that was not quite thick enough and opens a hole in the boundary between breathable air and absolute vacuum? What do we do when we are 400,000 kilometers from the nearest help and the system that was supposed to save us is the system that just broke? These questions are not asked out of pessimism. They are asked out of the same rigorous intellectual honesty that separates aerospace engineering from wishful thinking. And the answers, when they exist, are built into the vehicle. When they do not fully exist, something more uncomfortable takes their place. Accepted risk. Residual probability. The engineering euphemism for we have done everything we can, and beyond this point, we are trusting physics and fortune in roughly equal measure. The Orion capsule is the most thoroughly tested crewed spacecraft in NASA's history. That statement is both true and important, and it requires immediate qualification, because thorough testing and complete certainty are not the same thing. They have never been the same thing in the history of spaceflight, and the distance between them is where disasters live. Orion's design draws on the lessons of Apollo, Gemini, and Mercury, filtered through 50 years of computational advancement and material science. The capsule is a blunt-body re-entry vehicle, a cone-shaped craft specifically designed so that its geometry creates a bow shock wave during atmospheric re-entry, building up a layer of superheated plasma in front of it that the heat shield absorbs rather than the crew module. The Orion heat shield is the largest of its kind ever built for a crewed spacecraft, approximately 5 meters in diameter, constructed from a material called Koch, an ablative compound that chars and erodes in a controlled manner, carrying heat away from the vehicle as it does so. During the return from lunar distance, Orion will re-enter Earth's atmosphere at approximately 11 kilometers per second, roughly 40 times the speed of sound. At that velocity, the interaction between the capsule and the atmosphere generates temperatures on the heat shield surface exceeding 2,800 degrees Celsius. That is hotter than the surface of some stars. It is hotter than the melting point of steel, of titanium, of most materials that human industry has ever produced. The heat shield stands between that temperature and the crew module interior, which must remain within survivable ranges throughout the minutes-long re-entry. This system worked during the uncrewed Artemis II mission. The heat shield performed. The capsule survived. But in the post-flight analysis, engineers discovered something that did not appear in the pre-flight models. The ablative material had eroded in patterns that were not entirely predicted. In some areas, more deeply than expected. In configurations that suggested the re-entry aerothermodynamics were more complex than the simulations had captured. The capsule survived. The margins held. But the margins were not exactly where the models said they would be. This is the nature of operating at the boundary of known physics. The models are extraordinarily good. The computational fluid dynamics simulations, the wind tunnel tests, the arc jet heating experiments. They produce predictions of remarkable accuracy. But the universe, when presented with a 5-meter blunt body traveling at 11 kilometers per second through an increasingly dense atmosphere, finds combinations of fluid behavior and thermal interaction that no model, however sophisticated, has fully anticipated. And the difference between a heat shield that erodes slightly more than expected and one that fails catastrophically is a difference that can only be fully understood after the vehicle has flown. The crew of Artemis II will re-enter on that heat shield. They will trust it with their lives at 2,800 degrees. And they will do so knowing that its behavior under real lunar return conditions has been observed exactly once. On an uncrewed flight that revealed unexpected erosion patterns that engineers are still fully characterizing. But let us move deeper into the mission profile, because the re-entry is the last risk. Before it come the ones that are, in some ways, harder to escape. In low Earth orbit, an abort is a rescue. If something goes catastrophically wrong on the International Space Station, the Soyuz or Dragon capsules docked to it can return the crew to Earth in hours. The physics of low orbit mean that a return trajectory is always available, always relatively short, and always terminates at a planet with hospitals, surgeons, and the full resources of terrestrial medicine. At lunar distance, none of that is true. The geometry of orbital mechanics does not offer a quick road home from 400,000 kilometers away. The return trajectory from lunar distance is not a straight line. It is a carefully calculated arc through gravitational fields, requiring engine burns at precise moments, precise durations, and precise orientations to achieve a re-entry corridor. Narrow enough to succeed, but broad enough to be achievable. Miss the entry corridor too shallow, and the capsule skips off the atmosphere like a stone off water, rebounding into space with no second chance. Miss it too steep, and the vehicle decelerates too rapidly, generating G-forces and heat loads that exceed structural limits. The window for successful re-entry from lunar distance is, in physical terms, extraordinarily precise. The difference between a survivable and unsurvivable re-entry angle is measured in fractions of a degree. This is not a new problem. Apollo solved it, repeatedly, successfully. But Apollo solved it with a crew that had a functioning service module engine to make the corrections needed. The service module engine on Orion is the primary propulsion system for the mission, for trajectory corrections, for the lunar flyby maneuver, for the return burn that sets the capsule on its path home. If that engine fails at the wrong moment, the options available to the crew narrow with a speed that the word emergency does not adequately capture. The Orion service module, built by the European Space Agency, is a derivative of the automated transfer vehicle that served the International Space Station for years. It carries a main engine and a set of smaller auxiliary thrusters. The system is redundant in the sense that the auxiliary thrusters can, in some scenarios, perform functions the main engine cannot complete. But redundancy in engineering is not the same as redundancy in outcome. A backup system that can do 60% of what the primary system did is not the same as having the primary system. It is a degraded mode of survival, a narrower corridor, a harder problem. A crew managing a crippled vehicle with diminishing options, while 400,000 kilometers of vacuum separates them from the only planet that can save them. Apollo 13 is the historical precedent that mission planners and crew members carry with them always, because it is the closest the human spaceflight program has ever come to losing a crew in deep space and surviving. On April 13, 1970, an oxygen tank in the Apollo 13 service module exploded approximately 56 hours into the mission and 200,000 miles from Earth. The explosion destroyed the service module's power generation capability, its water supply, and its primary propulsion. The crew, Jim Lovell, Jack Swigert, and Fred Hayes, retreated to the lunar module, using it as a lifeboat for 4 days while the combined expertise of thousands of people on the ground worked to find a way to bring them home. They survived. The ingenuity was extraordinary. The improvisation was heroic. And the outcome was a testament to human problem-solving under conditions of extraordinary pressure. But consider the specific architecture of that survival. The lunar module was available as a lifeboat because Apollo 13 was a lunar landing mission, and the lunar module was already aboard, powered down but functional. It had its own propulsion, its own life support, its own power. It was, in effect, a second spacecraft attached to the first. An accident of mission design that became the instrument of survival. Artemis II is a lunar flyby mission. It does not carry a lunar module. It does not carry a second spacecraft. The Orion capsule and its service module are what the crew has, from launch to splashdown. There is no lifeboat. There is no backup vehicle waiting in the configuration. If the service module fails catastrophically, the options available are the options that exist within Orion. And Orion was not designed to be its own rescue vehicle. It was designed to work as intended. This is not a design flaw. It is a mission architecture decision made with full awareness of the trade-off. The mass and complexity of carrying a second propulsion system capable of returning the crew from lunar distance would fundamentally change the vehicle's design requirements. The decision was made that Orion systems, with their redundancies and margins, provided acceptable reliability. And they may well be right. Statistically, they are almost certainly right. But statistics live in the aggregate. They describe populations of events, not individual ones. The crew of Artemis II is not a population. They are 4 specific human beings, with names and histories and people who love them. And they will experience not the statistical average of all possible mission outcomes, but exactly one outcome. The one that actually happens to them. And the one that actually happens to them will be determined not by probability distributions, but by the specific, unrepeatable interaction of hardware, physics, human decision-making, and the irreducible randomness that complexity always introduces into systems operating at the edge of their design envelope. The micrometeorite environment at lunar distance adds another dimension to this calculus that is rarely discussed in public mission summaries. The space between Earth and Moon is not empty. It is populated by fragments of asteroids, comets, and the debris of 4.5 billion years of solar system evolution. ranging from dust grains to objects centimeters across, all traveling at velocities that make any impact a high-energy event. The probability of a significant impact on Orion during a 10-day mission is low. The shielding incorporated into the capsule walls is designed to mitigate the effects of small particle impacts. But there is no shielding that eliminates the risk entirely, because eliminating it entirely would require a wall of infinite thickness. The engineering approach to micrometeorite risk is probabilistic. You calculate the flux, the number of particles of various sizes expected per unit area per unit time in the region you are transiting. You calculate the probability that a particle of sufficient size to penetrate the hull will intersect the projected cross-section of the vehicle during the mission duration. You determine that this probability is acceptably low. And then you build the vehicle anyway and send people inside it, because the alternative is to never go anywhere. And that is its own kind of defeat. What the probability calculation cannot tell you is which mission, in the long sequence of missions that humanity will fly, encounters the one particle at the one moment that falls outside the acceptable envelope. It cannot tell you whether that mission is the 10th or the 100th or the 1000th. It can only tell you that somewhere in the sequence, in the fullness of time and missions, the distribution will produce an outcome that was always possible and was never, in any honest accounting, truly prevented. The crew of Artemis II inherits all of this. Every risk, every margin, every calculated probability, every design decision made in rooms they were not in, by engineers who are brilliant and fallible and human. They inherit the heat shield with its unexpected erosion patterns, the service module with its single main engine, the capsule volume of 9 cubic meters, the Van Allen belt transit, the solar maximum radiation environment, and the micrometeorite flux of interplanetary space. And they also inherit something else, something that does not appear in the risk assessments or the engineering documents or the mission profiles. They inherit the weight of being the first human beings in 50 years to stand at the edge of the deep black and look back at Earth from the distance of the moon. The weight of being the living proof that the species that built the pyramids and painted the Sistine Chapel and sequenced the human genome and split the atom is still capable of doing the hardest, most dangerous, most gloriously unnecessary thing it has ever done. That weight is not nothing. In fact, it may be the heaviest thing they carry. There are 4 names attached to this mission. 4 specific human beings who were selected from among the most rigorously evaluated candidates in the history of space medicine. People who passed through years of physical testing, psychological assessment, technical training, and the kind of quiet, sustained scrutiny that leaves nothing about a person unexamined. They are not abstractions. They are not symbols. They are Reid Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen. And before we speak any further about trajectories and radiation and heat shields and failure modes, it is worth pausing to consider what it actually means to be one of them. It means you have spent years preparing for a 10-day experience that no living human being has had. It means you have studied the mission profiles of Apollo astronauts who are now elderly or gone, reading their accounts, watching their interviews, trying to extract from their words some transferable knowledge about what it feels like to watch Earth shrink to a marble in the window. It means you have sat in simulators and run failure scenarios until the emergency procedures are not thoughts, but reflexes. Until the muscle memory of survival has been written so deeply into your nervous system that it executes before the conscious mind has finished processing the problem. And it means that none of that preparation fully answers the question that cannot be answered in advance. What does it actually feel like to be there? This question matters more than it might initially appear, because the answer has operational consequences. Human performance under conditions of extreme psychological stress is not a constant. It degrades. It shifts. It produces decisions that look, in retrospect, like obvious errors, but felt in the moment, like the only available choice. The history of aviation and spaceflight is full of accidents that had a human performance component. Not because the crews were incompetent, but because the human nervous system has predictable failure modes that emerge under specific combinations of stress, fatigue, time pressure, and environmental disorientation. The psychological environment of a lunar transit mission produces all of these conditions simultaneously. The crew will be sleep-deprived, because sleep in microgravity is physiologically disrupted. The fluid shifts, the vestibular confusion, the absence of a natural day-night cycle that the human circadian rhythm depends on all combine to reduce sleep quality in ways that accumulate over days. They will be physically deconditioned, because even 10 days of microgravity begins the process of muscle atrophy and bone density loss that the body initiates whenever it determines that gravity no longer requires structural maintenance. They will be navigating a cognitive load that has no terrestrial equivalent, managing complex systems, monitoring their own physiological status, communicating with a ground team separated by a 2-second signal delay. And doing all of this while their inner ears insist that the concepts of up and down have ceased to have meaning. And they will be looking out the window at something that the human visual cortex has no evolutionary framework for processing. The lunar surface from orbital distance is a landscape of absolute desolation. Gray, cratered, airless, ancient. A world that has not changed significantly in 3 billion years because there is nothing there to change it. No wind, no rain, no biology, no erosion in any terrestrial sense. Just the slow accumulation of micrometeorite impacts over geological time, pocking and gardening a surface that is simultaneously the most alien and the most familiar thing the human eye has ever encountered. Familiar because it hangs in our sky every night. Alien because it is a dead world and we have always known it, in some cellular way, to be a dead world. The psychological impact of seeing Earth from lunar distance has been described by every Apollo astronaut who experienced it. And their descriptions share a common vocabulary that transcends individual personality. The word most often used is small. Not beautiful, not fragile, though both of those appear as well. But small, the sudden, visceral, unignorable smallness of the planet that contains every human being who has ever lived, every war ever fought, every love ever felt, every idea ever conceived. All of it, compressed into an object you can cover with your thumb. Edgar Mitchell, who flew to the moon on Apollo 14, described the experience as a sudden, overwhelming recognition of connection. A sense that the molecules of his body and the molecules of the stars were part of the same continuous process. That the boundary between self and universe was less solid than it had always appeared from the surface. He spent the rest of his life trying to understand and communicate that experience, founding research institutes and writing books and giving interviews in which he struggled with evident frustration to translate a perception that language was simply not built to carry. Michael Collins, who orbited the moon alone in the Apollo 11 command module while Armstrong and Aldrin walked on the surface below, wrote in his memoir that he did not feel lonely during those hours of complete communication blackout on the far side of the moon. He felt, he said, awareness, a heightened, clarified sense of existing at a specific point in space and time that most human beings never reach. He was the most isolated human being in the history of the species during those orbits. separated from every other living person by the diameter of the moon itself. And he described it not as terror, but as a kind of profound, quiet aliveness. These testimonies matter not as poetry, but as data, because they tell us something about what happens to human consciousness when it is removed from all terrestrial reference frames and placed in a context of genuine cosmic scale. They suggest that the experience of deep space does something to human perception that is not captured by the training manuals or the mission profiles or the psychological screening protocols, something that changes the people who go through it in ways that are difficult to predict and impossible to simulate. The crew of Artemis II will experience this, all 4 of them, and they will experience it while simultaneously managing a complex spacecraft in a hostile environment, monitoring their radiation exposure, executing mission tasks on a timeline designed by people who have never been where they are going. They will be asked to be both explorers and operators, both witnesses to transcendence and technicians of survival, simultaneously and without pause. This dual demand is one of the less discussed design challenges of human spaceflight. The astronaut selection process optimizes for people who are exceptionally good at managing cognitive load under pressure, people whose emotional responses are well regulated, whose decision-making under stress is reliable, whose performance does not degrade sharply in adverse conditions. These are genuine and valuable human qualities, but they are also, in a subtle way, qualities that work against the full depth of the psychological experience that deep space produces. The person best suited to keep a spacecraft functioning in an emergency is not necessarily the person best suited to process the existential weight of what they are seeing outside the window. And the person most capable of feeling the full philosophical impact of floating 400,000 kilometers from Earth may not be the person you want at the controls when a caution and warning alarm sounds at 3 in the morning. The mission requires both, and it requires them from the same 4 people, at the same time, in the same 9 cubic meters. Reid Wiseman carries the role of commander, the person whose judgment, in any final analysis, governs the life of the mission and of the crew. The weight of that role in a lunar transit is qualitatively different from its weight in low Earth orbit, in ways that no amount of ISS command experience fully prepares you for. On the station, a commander makes decisions within a framework of options. There is always the possibility of return, of rescue, of additional input from the ground. At lunar distance, the commander makes decisions within a framework of finalities. There is no escalation path beyond what the vehicle can provide. The ground can advise, model, calculate, and recommend. But the commander aboard Orion is the last decision node in the chain. The human being whose judgment, when the models and the recommendations have been exhausted, is the only remaining instrument. Victor Glover brings to this mission something that extends beyond his individual biography into the long, complex, and often painful history of who has been allowed to go to space and who has not. He is the first Black astronaut to serve on a long-duration ISS mission, and he will be the first Black astronaut to travel to lunar distance. This fact does not change the physics of the mission. The Van Allen belts do not discriminate. The vacuum does not care, but it changes the human meaning of the mission in ways that physics cannot measure. Because representation in exploration is not merely symbolic. It is a statement about who the future belongs to, about which branches of the human family are included in the most audacious projects the species undertakes. Glover's presence on Artemis II is, in that sense, not an addendum to the mission's significance. It is part of it. Christina Koch carries her own form of historic weight. She holds the record for the longest single spaceflight by a woman, 328 days aboard the International Space Station. And that record is not merely a biographical footnote. It is a data point in the ongoing project of understanding what extended spaceflight does to the female physiology, which differs from the male physiology in ways that matter for space medicine and have been studied, historically, far less. Koch's body is a research instrument as well as a life. And the data her Artemis II mission generates about female physiology at lunar distance will inform the medical frameworks of every crewed mission that follows. Jeremy Hansen represents something equally significant in a different register. He is Canadian, the first non-American to be assigned to a lunar mission. And in that assignment, there is a quiet but unmistakable statement about the internationalization of deep space exploration. The moon is not an American destination. It never was, in any legitimate moral sense. It is a destination of the species. And the presence of a Canadian astronaut in the crew of the first crewed lunar transit mission in 50 years is a small but real expression of that truth. 4 people, 4 histories, 4 bodies carrying 4 unique physiological profiles into the same 10-day exposure to the same radiation environment, the same microgravity, the same psychological pressure, and the same risk. The same irreducible, carefully calculated, honestly acknowledged risk that attaches to every mission that has ever carried human beings beyond the surface of this planet. There is a tradition in the astronaut corps that outsiders sometimes find strange. Before a mission, crew members record video messages for their families, messages to be delivered in the event that they do not return. These messages are not morbid rituals. They are acknowledgments. They are the crew's way of looking at the risk with clear eyes and saying, "I see you. I have measured you. I have decided that what I am going toward is worth what I might leave behind." The families of the Artemis II crew have seen those videos recorded. Perhaps they have watched them. Perhaps they have deliberately not watched them, choosing instead to hold the knowledge of their existence at a careful distance, close enough to feel its weight, but not so close that it changes how they look at the person they love when they walk through the door each evening. This is the human cost of exploration that the mission profiles do not contain, and the press briefings do not address. Not the technical risk, not the engineering challenge, not the political and budgetary pressures that shape every NASA program, but the specific, personal, deeply private negotiation between ambition and love that every astronaut and every astronaut's family conducts in the months before a mission launches. The negotiation between knowing that the thing they are doing matters and knowing that they could be the one who does not come back. 4 people have made that negotiation. They have recorded their messages and trained their procedures and packed their equipment and reported to the launch complex. They have looked at every piece of data available about what they are flying into and concluded, each in their own way, that it is worth it. And somewhere in the depth of that conclusion, beneath the training and the professionalism and the extraordinary competence that got them to this point, there is something simpler and older than all of it, something that has nothing to do with engineering or physics or mission architecture, something that is simply human, the need to go toward the thing that frightens you, to stand at the edge of the knowable world and look over it, to carry the light of consciousness into the dark and see what it illuminates. That need is not rational. It cannot be fully justified by cost-benefit analysis or strategic national interest or scientific return on investment. It is older than those frameworks. It is the same impulse that drove the first human beings across land bridges and ocean straits and mountain passes into territories where no one from their group had ever been, where the maps ended and the unknown began. It is the same impulse that has always been both the most dangerous and the most defining thing about this species. And it is, in the end, why 4 people are preparing to leave the only world they have ever known and travel 400,000 kilometers into the dark, trusting their lives to a heat shield that has flown once, a service module engine that must not fail, a radiation environment that cannot be fully controlled, and each other. There is a building at the Johnson Space Center in Houston, Texas, where the walls hold photographs of people who did not come home. They are not displayed as warnings. They are displayed as memory, as the institution's way of carrying its dead forward into the work that continues in their names. The faces in those photographs belong to men and women who knew, with the same clarity that the Artemis II crew knows, exactly what they were risking, who made the same negotiation between ambition and mortality, who recorded their own messages and trained their own procedures and walked toward their own launch complexes with the same combination of discipline and audacity that defines everyone who has ever agreed to sit on top of a rocket. 17 of them did not return. That number, 17, is the weight that every NASA mission carries, whether it acknowledges it openly or not. It is the weight of Gus Grissom, Ed White, and Roger Chaffee, who died in Apollo 1 on January 27, 1967. Not in space, but on a launch pad, in a pure oxygen atmosphere that turned a small electrical spark into an inferno that killed them in seconds inside a sealed capsule with a hatch that opened inward and could not be forced open from the inside against cabin pressure. They died on the ground. They never left Earth, and their deaths were the first brutal lesson in what it costs to move too fast, to accept compromises that seem manageable until they are not, to let schedule pressure and budget pressure and the enormous political momentum of a space race override the slower, quieter voice of engineering caution. The response to Apollo 1 was a complete redesign of the command module, a 2-year halt to crewed missions, a systematic re-examination of every system, every material, every procedure. The hatch was redesigned to open outward in seconds. The pure oxygen atmosphere at launch